Okay, so let's see. We got 70 people who answered, and let's see what people said. All right, B intersect A, 0. Okay. Some people said 0 for this one. Then we got 0.1, 0.4, a couple different things. A given B, people said 1. 0 and 1, very strange. What is the correct answer? 0 and 1. The answers were 0 and 1. Okay, so 60% of people got 0 over here. How many people over here? Just under half the people got this one, which is 1. Reminder, 1 in probability means a 100%. So this one, A given B, is 100%. So if you have the correct Venn diagram here, you should notice something interesting going on, which is that one of the circles is completely in the other circle, right? So if you are a B, you are definitely an A. If you are, in this problem, if you have the B event, if B happens, then A definitely happens. And that is why this conditional probability, the chance of A happening, given that B happened, it's 100%, right? All of the B's are also A's. Vice versa is not true. Okay, Gary's going to show you with a nice Venn diagram here, this kind of thing. But so it looks like right around half the people got it. Maybe some people who didn't get it are still confused about what the line means. You must learn what the line means. Okay.
Okay,
So feel free to change it. Yeah.
Okay. Very first announcement. On course link, announcement today on the midterm being scheduled. We got our first requested date, but not our second. We have a room, which I'm hoping to get more space. They gave us the same room that we have in our classroom, but I wanted more space, so we just have more room to work. But the point is we do have confirmed dates for when we're going to have the midterm. If you write with the SAS Exam Center, get your request in, finalized, do it today, okay? And we will be announcing the location later on because, as I said, I'm going to request even more space than we currently have. We can get by with what we've got, but we like to have lots of space. You like to have lots of elbow room, right? But space is very tight at the university, so I'm not convinced we're going to get that. But again, you can check the dates and the times and the time of the test. It'll go. We'll be using a section in between 5:30 and 7 o'clock. One advantage to having it in the evening rather than the class is we can give you more time on the test. So if we were to do it in class, we could only give you about 35-40 minutes. So this will give us a little more time to work on problems. Okay, so that out of the way, let's go on to the class of the day. And we're going to go through. These are pre-posted on the, they went up just before class. They're pre-posted on CourseLink. And without a bunch of additions. So if you want to follow on those. And what I want you to do is, maybe the odd thing write down, but most of the things you're going to be able to kind of like just make sense of what's going on here. So what I'm going to do is run through what I call the yellow, orange, red series of Venn diagrams. And we're going to start off with this initial, two initial probabilities, a P of A and a P of B. P of A being 0.5, a P of B being 0.4. And we're going to hold those in all cases here. And I'm just checking out why that thing has gone off. Okay. So we're going to watch the following colors. When you see an orange area, it's going to be the probability of A intersect B, because that's what happens when we overlap a yellow with a red. And so if you get a pure yellow, you're in A but not in B. Red, you're in B but not in A. And there's going to be a gray area outside of the circles, outside of the union. And it's not to scale, but the circles themselves are to perfect scale. Okay, so again, the total area of the sample space, it's a probability is 1. And so we're going to start off with this one, which we just saw in class on the mathematized questions, where B is actually a subset of A. So A is bigger than B, so B is entirely contained within A. And note that if you are in B, you must be in A. So the probability of A given B is going to be 1. Okay, you can also ask yourself then, what's the probability of B given A? Well, that's something to ask yourself. Now, what I'm going to do is pull these circles apart a bit, and I'm pulling them a little bit apart here so that the area of the intersection is now 0.3. Yes, they overlap, but there's areas where B occurs without A and A occurs without B. And again, you can go through and notice that there are 4 intersections here. A intersect B, A intersect not B, not A intersect B, or if you want to call it B intersect not A, that's the same thing. And then the gray is the not A intersect not B, or A complement intersect B complement. Okay, and those 4 intersections compose the entire sample space. They are both mutually exclusive, but they're also exhaustive. Okay, so those 4 intersections are all mutually exclusive, but they also exhaust the sample space. Now we'll go one more along here, and well, I want to come back to this one a little bit first before I go on to the next one. How do we know that events A and B are independent? Well, that's a kind of a good question, and well, there's various ways we could look at that, but if I wanted to know, for example, the probability of A given B, well, maybe I'll just sketch it out here. Let's see if you could sketch it out.
Gonna flip on the dot.
Yeah, I'm gonna flip on the dot camera, but not at the moment. Everybody's writing everything down. What I want you to do is find the probability of A given B, and well, that'll be sufficient, I think, is the probability of A given B. Okay, for this diagram, and I'm just gonna redraw it here. So, it's not exactly the scale. In fact, I really got it off the scale because I may be bigger than A, but that's besides the point. So I'm going to go to the dot camera here for a second. So I drew that diagram out again on the dot camera, and again, this is A intersection B, and what was that probability? It's given to us as 0.30, 0.30, and we know the probability of A was 0.50, and the probability of B was 0.40, so we can go through and finish everything else in our on our Venn diagram. This area out here, A intersect B complement, its probability is 0.20. Get that again just by subtraction, because the total area of A is 0.5. So 0.3 is in the intersection, 0.2 is over here. And over in this one, the probability of B is 0.4, 0.3 falls in the intersection, so 0.10 falls out there. And that is your A complement intersect B. And just to be complete about things, 0.2 plus 0.3 is 0.5, another 0.1, 0.6. This area out here, which is A complement intersect B complement, has an area of 0.40. Okay, so we got all nice things. So now we want the probability of A given B. Well, the probability of A given B, once we are saying you're given B, again, the condition is the first thing you focus on and say, where does B occur? It occurs right there. It occurs with probability 0.4 in the full sample space, but now I'm given B. So that becomes my denominator, the probability of B. And then we say what proportion of B occurs with A. That occurs in the intersection, the probability of A intersect B. So that's going to be 0.30 over 0.40 equals 0.75. So are A and B independent? The answer is no. No. Why? Because the probability of A given B does not equal the probability of A. Okay, so that tells us right away that they are not independent. There's other ways we could have tested for independence. We could take the probability of A times the probability of B and say it's 0.2, and that's not equal to the intersection that was given to us. So again, that's another way to test that they're not independent. Also note, the probability of A times the probability of B does not equal the probability of A intersection B. Okay. So again, that's another way of testing. And we have many ways of testing for independence. If one of them is shows that they're independent, A and B are independent, they all will show that A and B are independent. Any questions on that so far? Other than trying to read my writing, which makes you concentrate hard, right? Okay, on to our next diagram. Now this one here, it says the events A and B are independent. And how do we know that? The probability of A times the probability of B is equal to the probability of A is 0.5, the probability of B is 0.4. Multiply them together, it's 0.2, and we are told that the intersection is 0.2. And so notice that when A and B are independent, the circles must overlap, but the fact that the circles overlap does not prove that they are independent. The overlap must be exactly the right size. That's the key thing, is that the overlap has to be exactly the right size. And that right size is the product of the two unconditional probabilities. Anything else, they're not going to be independent. So I'm going to pull those circles a little further apart. Now, if we were, well, actually, just let me draw one more picture here. Going through the same picture that we just went through. Sort of. Oh, bigger this time. More, better thing, better scale, but it doesn't really matter. Okay, sample space, total area is 1, and we're told this is 0.20. So again, that's B. And so this area out here is 0.20, and this is 0.30, and this area out here is 0.30. And you can go through and label each of these intersections, okay? So you go through and you say, yeah, that's A intersect B, and that's A complement intersect B, and that's A intersect B complement, and this is A complement B complement. And if you get used to doing these Venn diagrams quickly, you get to really be able to twist things around in your brain really quickly. Okay? But let's just take a look at one question. The same question we asked last time is to find the probability of A given B. And okay, we're told that B's occurred, so I'm going to take the probability of A intersection B over the probability of B. And that's going to be 0.20 divided by 0.40 equals 0.50, which is simply the probability of A. Okay, so knowing B occurred told us nothing about the occurrence of A. If we know nothing about B, the probability of A is 0.5, but knowing that B occurred, the probability of A occurs is still 0.5, and that's why A and B, that's a test for the independence of A and B. Similarly, you could have found for example, the probability of A given B complement, and that would have been the probability of A intersect B complement over the probability of B complement. Oops, what's that C doing down there? And you would have said A intersect B complement is 0.30 over the probability of B complement. Well, the probability of B is 0.4, so the probability of B complement is 0.60. But again, you notice that's 0.50, which is just the probability of A. Okay? So you can go through, you can look at the probability of B given A, you can look at the probability of B given A complement, you can do all kinds of complements. The point is that the condition gives me no information when we have independence. Now, come out one more intersection here. Things are still overlapping. I cannot look at a Venn diagram with overlapping circles and just say, oh, they are overlapping, they're independent. No, that doesn't work because I have to test whether that intersection is exactly the right size. So these are overlapping, but are they independent? Well, one simple test, 0.5 times 0.4 gives us 0.2. That's not equal to the probability of A intersect B. So, no, they're not independent. We could go through and work out the conditional probabilities for those ones. And, well, maybe we could do that. It doesn't take us that long. Because we get pretty good at sketching our Venn diagrams and saying, okay, that's 0.10 in there, and so that leaves 0.30 in there, and that's 0.5, 0.1 there, so that leaves 0.40 there, and that thing, 0.4, 0.5, there, 0.8, that leaves 0.20 there. And again, we could go through and label things, but the thing is, if I want the probability of A given B, I would take the probability of A intersect B over the probability of B, and so I'm going to take 0.10 divided by the probability of B, which is 0.40 equals 0.25, and you know, because it's kind of fun, the probability of A given B complement, let's work that one out. That's going to be the probability of A intersect B complement over the probability of B complement, and that's going to be A intersect B complement is 0.40 over the probability of B complement, which is 0.60, which is 2/3. Actually 0.67. Note the probability of A does not equal the probability of A given B, and the probability of A doesn't equal the probability of A given B complement. There's something else that's actually a little interesting to note, is that if I know nothing about whether B occurs or doesn't occur, whether it will occur or will not occur, the probability of A is 0.5. But if I know that B's occurred, that B's definitely going to occur or B has occurred, I lower the probability that A will occur. My assessment of A occurring, that probability drops from 0.5 down to 0.25, but if I knew that B that didn't occur or is not definitely not going to occur, the probability that A occurs actually goes up from 0.5 to 0.67. And so what we see is how having information about B, in this case, gives us information for revising my probability of A. In the case of when we had independent events, no, we didn't have such information. And we can go a little further, okay? And again, you can go through, work these out. So again, there's an intersection in there, but they're still overlapping. But again, the probability of A times the probability of B, which is 0.2, is not the same as the intersection. And we can go even like just a little bit of an overlap, okay? Only 0.01, but the point is they're not independent, they're dependent. In fact, we had all kinds of intersections there for which we didn't have independence. And here's a very extreme one where, in fact, they have gone to the point that they are mutually exclusive or disjoint. Okay? If A occurs, B doesn't occur. In other words, if you're in A, you can't be in B. And if you're in B, you can't be in A. Okay? So that is still a form of dependence, because the probability of A times the probability of B, again 0.2, they have to have an intersection of size 0.2 if they're independent, and it's 0. So mutually exclusive events are automatically dependent events. And that's what often gets confused. We have some interesting examples of this in places that should know better. But again, just think of it as if, do we have information about B if we're in A? Yes, we know that B can't occur. If I know I'm in B, do I have information about A? Yes, I know that A can't occur. So we can go back and just kind of like look at, we went from the point where B was a subset of A, and then we went blink, 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 to the fact that they were disjoint. And there was only one place there where A and B were independent, and that was the situation where the product of the two unconditional probabilities gave us the exact size of the intersection. Okay, I'm going to just go there. So here's something to do. Good practice is just to go through, and for each of those diagrams, and you can do this quite quickly once you catch on, is work out the probability of A intersection B, the probability of A union B, the probability of A given B, the probability of B given A, state whether they are dependent or independent events. We have gone through that. label whether you've got any special cases, such as a subset or mutually exclusive events. And you can do other optional headings. And what I mean by optional headings, maybe you want to do something like the probability of A given B complement, or the probability of B given A complement, or the probability of not A given B. There's lots of other possibilities you could do. Okay, and it's the comparison of these that gives you useful things. Okay, so those were Venn diagrams. Now, Venn diagrams were named after John Venn, who was a British mathematician. I've seen a quote that nobody has ever become so famous for such a trivial bit of mathematics that he figured you could overlap these circles and that kind of thing, you know. Celebi, we'll have maybe a little more to say about John Venn later on. Some argue that a full Venn diagram has all intersections lit on the diagram, even if they are empty, and that the better name for these diagrams are Euler diagrams, but, you know, that's kind of like, I don't know, semantics. You know, you go with diagrams that are nice, but I'm going to show you another. So I often use the term Venn-like diagrams. So there's another type of diagram I really like, is what I'll call Venn-like diagrams involving rectangles. So I'm going to come up with that. But before I do that, I just want to show you a Venn diagram for 3 events, and these are all perfectly proportional for the probability of A given, for the probability of A, the probability of B, the probability of C, and all events are independent, and the circle areas are proportional, the outside area isn't. But again, you could go through and label all of these intersections, of which the very center is A intersection B intersection C, and then you can go through and, for example, you know, the probability, well, you need some colors. You need some colors matched up what they are. What did I come up with? The A was the yellow. Well, it starts off yellow here, but it's only yellow when we have A intersect not B intersect not C. And this one is not A intersect B intersect not C. And then here, what have you got? You've got A intersect B, intersect not C, and so on. Okay, so kind of just go through and label those things up on your own there. And again, the A intersect B, intersect C in the center. We can do some things with 3 events. We will have more to say about that. Okay, so what's the next up? I want to draw some what I call Venn-like diagrams composed entirely of rectangles. And I'll come over here. And the beauty of these rectangles we will show you is you can do complicated problems quite nicely with these kind of diagrams. They're very easy to visualize. It's easy to get things in proper proportions. So I'm going to start off, and I'm going to use the probability of A being 0.6, and so the probability of A complement is 0.4. So I'm simply going to take a sample space, you know, area of 1, and partition it up into 2 pieces proportional to the probability. So I've set this so this A is exactly 60% of S. In other words, it's got an area of 0.6, and then this should have had a little c, but I used a complement because I made a mistake. Because I like the little primes, but I'm trying to stick with the little c's. Okay, so just say that's little c. I'll fix that in the final slide, or I'll pre-post that. Okay, and I did this one too. So I'm going to do a probability of B, and I left the complement on the B as well. Okay, anyhow, the probability of B is 0.7 and the probability of B complement is 0.3. So what we're going to do is take those two rectangles and put one on top of the other. And if A and B are independent events, I can simply oppose the one set of rectangles on top of the other, and everything just kind of like fits really nicely along there, and I can get all of the intersections. They're all perfectly area proportional, and we can get all those intersections by multiplication. Probability of A intersect B is the probability of A times the probability of B is 0.42. And in fact, this rectangle is exactly 42% of the whole rectangle. Okay, and I can go through and get each of these. Probability of A complement intersect B. Probability of A complement times the probability of B is 0.28. And that's exactly 28%. And probability of A intersect B complement. Probability of A times the probability of B complement, 0.18, that's 18%. And then this intersection over there, probability of A complement intersect B complement, take the probability of A complement multiplied by the probability of B complement is 0.12. So here's another way of kind of thinking about this, is that, remember, A was 60%. A was 60% of the sample space S, which is an area of 1. And then what we're doing with independence is we're saying 70% of that space is covered by B, 30% is covered by B complement. That holds both in A and it holds in A complement. So 70% of A, 70% of A complement. It doesn't matter whether an A or A complement. I've got 70%. So if I know nothing about A, that's still 70% of the whole sample space. But if I know I'm in A, the part which is B is still 70%, and the part which is in B in A complement is still 70%. That stays 70%, 70%, very easy. So nice thing is, nice intersecting vertical and perpendicular lines there. Now, if we have a situation though where we have non-independence, we have a trickier diagram to draw. There's a couple different things we can do. I'm going to keep it as rectangles. So what we're going to do here is set, again, the probability of A and the probability of B as they were for the first case where they were independent. But now I'm going to give a couple conditional probabilities which are not the same as unconditional probabilities. So I'm going to tell you the probability of B given A is 0.6 and the probability of A given the probability of B given A complement, I've got another little one to switch, is 0.85. And so that's going to mean automatically that these are dependent events because the probability of B is not equal to the probability of B given A. Similarly, the probability of B is not equal to the probability of B given A complement. So it's trickier to do the diagrams now because I can't just do A separately and then do B separately and then dump them on top of each other. I've got to kind of like solve all of my areas. So the probability of A intersect B, I take the probability of A times the probability of B given A, and let's just take a look at that. The probability of A is 0.6 times the probability of B given A is 0.6, so I take 0.6 times 0.6 is 0.36. Okay, does everybody see where that numbers came from? Are we good with that numbers? Okay. And the probability, so what I've done here is A was 60%, but B, given I'm an A, is 60% of this 60%, so that's 36%, 0.36. You could get this part by subtraction, because you know this is 0.6, and therefore, if 0.36 is there, 0.24 is there. I can also calculate that directly. I can take the probability of A times the probability of B complement given A, that's 0.24. Okay, so that's 24%. And then over here, when I'm not in A, which is 40%, when I'm not in A, the proportion, which is B, is 85%. So what I'm saying is I want 85% of this, 85% of this, 0.85 times, 0.85 times A complement, which is 0.4. 0.85 times 0.4 gives us our 0.34. And that's going to leave, if we've got 85% of A complement being covered by B, we have 15% not covered by B. In other words, it's in B complement. So this is going to be 15% of 0.4, 0.4 times 0.15 is 0.06. 0.06. That's that. So that was one construction of the diagram. Okay? So I haven't actually really explained, I showed you the final result. Let me show you how I constructed the diagram. So what I did was I started off by drawing an A and an A complement, but then for A I take 60% of the red triangle, and for A complement I take 85% of the white triangle, and then I overlay them to get this one here. An alternative solution is, so that was the previous diagram. An alternative solution is to lay out B first and then say, okay, what do I want to do there? Well, B is B is 0.70, and A is 18/35 of that, which is about 0.514. And so I can go through and work out each of these intersections. I'll just let you go through and calculate those numbers and say when we superimpose them, we come up with that particular diagram. Okay? So we'll let you work through those. Now, I wanted to. Did you want to have anything you would have to want to get in today?
No, I'm
Well, you're good.
Yeah.
He's rolling on. Mihai's rolling on Wednesday and Friday. Rolling. Don't miss it. Like, do not miss it. My goodness. Okay.
I did have a question for you, Gary.
Yeah.
Can you go back a couple?
Go back a couple.
Yeah. Go back two more. One more. Yeah, stop here. So, this is like a 1 by 1 square, right?
Yep.
One on the bottom, one on the top. Total
Yep.
area is 1.
Yep.
We know A is 60%.
Yep.
So does that mean this length is 0.6? If I was going to get a ruler.
If
have
you
a ruler.
want, yes, that is 60%. That is 0.6.
0.6.
Precisely measured.
Okay, because we're measuring areas, and now all of a sudden we got a length. See?
Yeah.
The length is 0.6. And then this one would be 0.4.
That will be 0.4.
Okay. Here's a question. What if I measure this length? What would that be?
What would that length be?
Let's let everybody think about it. What is this length? So you get a ruler, you measure this length. You did all this stuff with areas, but what about lengths? That's what I want to know. This length. Everybody take 1 minute. Talk to your neighbors. What is this length? And then follow-up question, what is this length? Okay? Take a minute, think about those lengths, and we will draw. You were finished, right? Or did you have something else?
I have something else.
Okay. I looked at your slides and I noticed you got to the end, so I thought maybe.
I was going to take it.
Let's let them do this because I feel like the change gears. We won't get it.
I can do it.
Okay, let's come back together. Does anyone know what was the... I don't have a guess. You can put your hand up if you know what is the tall height. If you know what this tall height is. Yeah, in the second row.
0.85.
It's 0.85. 0.85. And actually, it's right there in the stuff that's given to us. Look, we were told that the probability of B given A complement is 0.85. That means when you're in this strip, 85% of this strip is supposed to be B, and 15% is supposed to be not B. Well, how do you take a strip and divide it up so 85% is one way and 15% the other way? 0.85 here, 0.15 here. What about this height? What if you take a ruler and measure that one? Anyone know? Anyone else know what that one is? Someone? Yeah. 0.7. I don't think it's 0.7. 0.7 is something else. 0.7 is going to be the ratio if you take all of the B's. So if you take all this shaded area, that shaded area is going to be an area of 0.7. So there is a 0.7 in the picture. It's the two rectangles together. But this height, the small height, is something else. Yeah. 0.6. Yes, 0.6. And that's because we were told the probability of B given A is 0.6. So if you're in the A strip, you need to be 60% of it needs to be B, and 40% is not B. And that's how, you know, all these areas that Gary was doing over here were areas of these rectangles. He didn't tell you the picture with the widths and the heights. What he's doing, rectangle is one number times another number. One number is the height, one number is the width. That's how he got all these areas.
And let's just go. That one.
Yeah.
And that was 0.34. So the areas, looking at that, again, this was the A intersect B. This was the A, this is the A complement intersect B. And when you add that and that, there's the 0.7. That is the probability of B.
All right, so that's what happens when they're not independent. When they're independent, it's a nice straight line. When they're not independent, you get two heights. All right, I guess we'll stop there. I'll see you guys on Wednesday.
So I can put some practice questions for them.
Yeah, if you want to
put some
give me some, I can turn them into homework questions.
I can turn them into there. I can gives you extra practice questions for the midterm, that kind of thing.
That's great.
And then